Welcome back. So far we have studied diffusion in single phase systems, or we have studied single phase diffusion, which means the terminal alloys which were used for diffusion couple both had same phases to start with, and there was no new phase forming during the course of the diffusion. Now next few classes I would like you to we would study multi-phase diffusion. In multi-phase diffusion, either we start with two terminal alloys which have two different phases, or even if we start with two terminal alloys having the same phases, during the course of diffusion a new phase or a multi-phase layer forms in the diffusion zone. While studying multi-phase diffusion, we would often refer to ternary isotherms, and hence in this lecture I would like you to briefly introduce to ternary phase diagrams with the focus on how to read ternary isotherm, because that is more important through our class's perspective. In a binary system there are two concentration variables, out of which only one is independent. Hence a ternary phase diagram has to be plotted in 3 dimensions, in which temperature is plotted on a vertical axis and two independent concentration variables on the horizontal axis. Typically this is how a ternary phase diagram is plotted. At the base of the diagram there is an equilateral triangle which represents 3 concentration variables. So triangle ABC here is an equilateral triangle. Corners A, B and C represent 100% of pure elements A, B and C, and on the vertical axis temperature is represented. The sides of the triangle represent the binary compositions. So side BA represent binary composition of system BA, AC represents the binary composition of the system AC, and CB represents the binary composition of BC. So I have shown the base of the ternary phase diagram here. This is usually referred to as the ternary triangle or a Gibbs triangle. We will see how the compositions can be read on this ternary triangle, but before that I would like to explain how the ternary phase diagram is constructed. So in this triangle each of the edges represent binary systems. Let us simply consider the simple eutectics. So let us assume that all 3 of the binaries are simple eutectic systems, and I have shown this simple eutectics on the sides. So this is the eutectic system AB, this one is eutectic system BC, and this is the eutectic system AC. If I make these binary phase diagrams stand vertically on the respective edges and extend various phase fields into the ternary compositions, it will form a ternary phase diagram. Remember, any composition that lies inside the triangle is a ternary composition. So if I make these binary phase diagrams stand up on the edges, it would look something like this. I have not shown the extension of the phases on this diagram into the ternary compositions as yet. Since all 3 systems are simple eutectics, there are 4 phases in all on this phase diagram. The 3 solid solutions alpha, which is basically pure A, beta which is pure B, and gamma which is pure C. And the fourth phase is liquid. We can see there are 3 eutectic points, one for AB, one for BC, and one for AC here. So, if we extend the liquidus of all the binary phase diagrams into the ternary composition range, then it will form basically the liquidus surface of the ternary phase diagram ABC. So, if I roughly do this, I can extend this is basically the liquidus surface. If I mark the isothermal sections on these liquidus surfaces, so this is how the ternary phase diagram ABC would look like from the top. So, basically a ternary phase diagram is a triangular prism with each face of the prism representing a binary system. So, I have redrawn this ternary phase diagram here. We can note there are 3 binary eutectics here. A binary eutectic is a 3 phase equilibrium, and these 3 eutectics are one on the binary system AB. Let us write the ABC corners here. In binary AB, the eutectic reaction is liquid going to alpha plus beta. In BC, the eutectic reaction is liquid giving beta plus gamma, and in AC it is liquid giving alpha plus gamma. In a binary phase diagram, a eutectic is an invariant. That is because of the constraints put by the Gibbs phase rule. So, if we write the equation for Gibbs phase rule, it says F is equal to C plus 2 minus P. Since I am considering phase diagram at constant pressure, so this would be C plus 1 minus P, and in a binary eutectic there are 3 phases in equilibrium. So, we have for 3 phase equilibrium F is equal to C plus 1 minus 3, which is C minus 2. So, this shows that for binary F is equal to 0. That means there is 0 degree of freedom for a eutectic equilibrium on a binary phase diagram. However, in ternary, since C is equal to 3, so we still have 1 degree of freedom, and hence a binary eutectic in a ternary phase diagram solidifies over a range of temperature. So, if I have highlighted the ranges of 3 different binary eutectics by the arrows here. So, if I denote these lines as, let us call this M is N and this binary eutectic point as L. So, the lines M O and where the 3 lines intersect is point O. So, the line M O, N O and L O, which are going down, represent the solidification range of ranges of the binary eutectics of alpha binary eutectics, including phases alpha beta and beta gamma and alpha gamma respectively. The 3 binary eutectics intersect at this point O, and it represents a ternary eutectic. A ternary eutectic has 4 phases in equilibrium. So, this ternary eutectic O represents the reaction liquid gives alpha plus beta plus gamma. If I apply Gibbs phase rule for ternary eutectic, here we will see F is equal to 0. That means, on a ternary phase diagram, a ternary eutectic or a 4 phase equilibrium represents an invariant. That means, it occurs at a single composition and single temperature, and hence a ternary eutectic solidifies at a single constant temperature. Now, this is a very simple case where we considered all 3 binaries to be simple eutectics, but there may be more intermediate phases forming, but there may be number of intermediate phases forming in each of the binary system. Also, there may be some ternary phases which may be forming, and hence the ternary phase diagrams may become very complicated. However, our interest is not studying. However, for this class we are not interested in studying the ternary phase diagrams in depth, but we are only interested in knowing how to read ternary isotherms, so that we can use it later on when we study multiphase diffusion. So, I would now briefly introduce you to how to read ternary isotherms. As the name suggests, a ternary isotherm is nothing but an isothermal section of a ternary phase diagram, and since a ternary phase diagram is a triangular prism, an isothermal section should be an equilateral triangle, and I have shown one such triangle here, ABC. Now, how to read the composition of a point inside a Gibbs triangle? So, let us consider an example of point P here. For doing this, I have to first draw 3 lines passing through point P and which are parallel to the 3 edges of the triangle. So, I have drawn line PP prime which is parallel to side BC, QQ prime parallel to side AC, and RR prime parallel to side AB. The compositions are expressed. The compositions can be expressed either in wet fraction, wet percent, or mole fraction or mole percent. In this case here, I have shown the compositions in wet percent. So, the wet percent of component A in the alloy with composition P is found by finding the ratio of length of BP and the length BA, or equivalently finding the length CP bar and taking the ratio with the length CA, finding the length CP prime and taking the ratio with the length CA. Similarly, the concentration of B in the alloy P is the ratio of length AQ prime with the length AB, or equivalently the ratio of length CQ with the length CB, and the concentration of C is the ratio of length AR and length AC, or the ratio of BR prime and BC. There are only 2 independent variables. So, the third concentration need not be evaluated this way, because the third concentration variable would simply be a dependent variable. So, the concentration of C can also be evaluated as 1 minus mole fraction, wet fraction of A minus wet fraction of B. For ease of reading, the sides of the Gibbs triangle are usually divided in equal divisions, so that we can mark the compositions easily. So, I have shown it on this triangle here, ABC, and I have shown the divisions for 20 mole percent here. As I said, unit can be mole percent or wet percent. One has to be consistent throughout the phase diagram. Note that any line parallel to an edge represents a constant concentration line for an element which is opposite to that edge. So, for example, if we consider line PQ, it is a line on which the concentration of B is constant. More specifically, line PQ here represents a 60 mole percent B line. So, any alloy that lies on this line PQ has concentration of B as 60 mole percent. Similarly, there is another line I have shown XY which is parallel to line BC. Any alloy that lies on line XY has a constant concentration of A which is 20 mole percent of A. Now, PQ and XY, they intersect at point R, and so the composition of alloy R would be 60 mole percent of B, 20 mole percent of A, and 100 minus 60 minus 20, which is 20 mole percent of C. This is how we can read the composition in a ternary triangle. So, I have covered all these points. Now, when there are more phases present, ternary isotherm may become little more complicated. One example I have shown here. In this case, all the binaries have terminal solid solubility. So, again I have shown the ternary system A, B, C. If you consider A rich corner, both the binary AB and AC have some terminal solid solubility on the A rich side, that is C is soluble in A to some extent, B is soluble in A to some extent, and the corresponding phase is labeled as alpha. And this solubility also extends to some extent into the ternary compositions, and hence on the A rich side you will see there is a single phase solid solution alpha. Similarly, on the B rich side there is a single phase region beta, and on C rich side there is a single phase region gamma. Between any two single phase regions there has to be a two phase region. So, between alpha and gamma we have alpha plus gamma, between alpha and beta we have alpha plus beta, and between beta and gamma we have beta plus gamma. You will see there are multiple parallel looking lines plotted in each of the two phase regions. These are nothing but tie lines. A tie line joins the two compositions which are in equilibrium. So, if we consider this red tie line here shown in alpha plus beta region, let us call this line as PQ. If you select any composition, let us say R here along this tie line, at this temperature the alloy R exists as two phases, exists in two stable phases. Alloy R exists as a two phase mixture, one phase alpha with composition P and the other phase beta with composition Q. If I change the alloy composition anywhere along this tie line, the phase compositions remain same. The only thing that changes, are the phase fractions of alpha and beta, and we can find the phase fraction by applying lever rule. So, if I want to find the phase fraction of alpha at composition R, it would be simply F alpha is equal to QR over PQ, and phase fraction of beta would be length PR over length PQ. Now, when I consider binary phase diagram, at a given temperature I can draw only one tie line, but on a ternary isotherm I can see there are multiple tie lines in the same two phase region. So, if I apply Gibbs phase rule here, I can write F is equal to C plus 2 minus P, and since the phase diagram is always at constant pressure, and since I am considering an isotherm or isothermal section of the phase diagram, I am holding temperature also constant, and so I do not need to consider factor 2. For a ternary, C is 3, and a two phase region, P is equal to 2, and so F is equal to 1. So, in two phase region on a ternary isotherm there is 1 degree of freedom, and hence there are multiple tie lines. There is also a three phase region here that you can see alpha plus beta plus gamma, and now I will talk about this three phase region. If I apply the Gibbs phase rule to the three phase region, obviously on a ternary isotherm the degree of freedom becomes 0. That means if there exists three phases in equilibrium at a constant temperature, their compositions are fixed. In other words, if I select any composition in this three phase region which is denoted by x, y, z here, I know that there exist three phases in equilibrium: alpha with composition x, beta with composition y, and gamma with composition z. And again that is because the degree of freedom in the three phase region is 0 on a ternary isotherm. With change in composition within this three phase region, the only thing that will change are the phase fractions of individual phases. The compositions of the phases remain same. Since the degree of freedom is 0, hence the three phase region on a ternary isotherm is usually triangle. The corners of the triangle represent the equilibrium compositions of the three phases. The only thing that changes with alloy composition within this triangle is the phase fraction. With change in alloy composition within the triangle, the phase fractions of three phases will change, but the compositions of the phases will be still. So, how do we find phase fractions? Again we can apply the lever rule as applicable to the tie triangle. So, if I consider point P here, in order to determine the phase fractions in alloy with composition P, I have to first draw three lines which pass through point P and one of the corners of the tie triangle. So, I have drawn the three lines passing through P, is x to small x, y to small y, and z to small z, and the phase fraction of phase alpha is then given by the ratio of length px and length xx, so px over xx. Similarly, the phase fraction of beta is length p small y over length big Y yy, py over yy, and the phase fraction of gamma would be pz over zz. This is how ternary phase diagram can be read. Now, there may be intermediate phases forming, and we may have more complicated looking ternary isotherms. One such example, not so complicated though, but having intermediate phases, I have shown here. This is a ternary isotherm of copper, nickel, zinc at 775 degree centigrade. This is not a very accurate isotherm. I am just showing the schematic which I have drawn. We can see the three corners: nickel, copper, and zinc. We know at 775 degree centigrade copper nickel system shows complete miscibility, and that miscibility extends quite a bit into the ternary composition range, and hence we see a big alpha FCC phase field here. Then there are multiple intermediate phases both in nickel zinc binary and copper zinc binary, and they show complete miscibility, couple of them, beta for example and gamma. And of course there is at 775 degree centigrade zinc exists as stable liquid, and so on the zinc rich corner we can see the single phase region of liquid or L. Similarly, there is a small composition range of a phase beta prime on the nickel zinc binary. This beta prime exhibits a small solubility for copper, and hence there is a small region of beta prime. Between any two single phase regions there would be two phase region, and so we can see the two phase region alpha plus beta here, then beta plus gamma, liquid plus gamma. Similarly, we have alpha plus beta prime here. This one here is beta plus beta prime. In each of the two phase region we can draw the tie lines which would roughly look like this. So in alpha plus beta the tie lines may look like this. In beta plus gamma they may look like this. Liquid plus gamma, and the tie lines basically join the equilibrium compositions of the two phases in equilibrium. Now for the precise tie lines one needs to experimentally determine those, but these tie lines would roughly look like this. There also exists one three phase region here. So there is a tie triangle here which is basically the three phase equilibrium of alpha, beta and beta prime. So this is the copper nickel zinc ternary isotherm at 775 degree centigrade. There may exist more such intermediate phases which may not show the complete solid solubility as exhibited by this beta and gamma here, and we can have more and more complicated ternary isotherms. We will do some of them in the exercise. This was just an example that I wanted to show so that you know how to read ternary isotherms. I will stop here today. Thank you.